And so we're going to get started with chapter 6, integer linear programming. This is the extension version of linear programming. So in the previous chapters, we had the solutions which are fractional numbers. But in chapter 6, we're looking for integer variables as a solutions. So even our fractional numbers and sometimes integer variables will be mixed with the fractional numbers. So first, so you're familiar with the linear programming, then our solution will be integer variables. So when it comes to integers, so you see 0, 1, 2, these kind of integers. And if your solution is only 0 and 1, we call it binary. Binary integer solution. And so you may have integer solution with fractional values. So this is kind of mixed integer linear programming. So you're going to see 3 different types of integer linear programming. So as we go, you may have several different examples with pure integer programming, binary integer programming, mixed integer programming. Okay, so when one or more variables, comes over decision variables, right? Decision variables in a linear programming must assume integer value. We have an integer linear programming problem. So this kind of problem can be found among scheduling workers, employee scheduling, and truck scheduling, and train scheduling, airplane scheduling, manufacturing airplanes, manufacturing equipment, installation of manufacturing equipment, because you cannot just install 1.2 equipment, 1.3 people, things like that. So that's why we're trying to find integer solutions. So integer variables also allow us to build more accurate models for a number of common business problems. So sometimes if you don't need exact number of the solutions, you may just have fractional numbers using linear programming with simplex method. But many business cases will need integer solutions. Yes, this is the example we had in the past. I'm going to draw the graph over here. Okay, x1 is x2. And we have 3 different resources. And then 12 students are in the waiting room. Joining. Okay. Now, so 1x1 plus 1x2 should be less than or equal to 200. 100 and 9x1, 6x2 less than or equal to 1566. There might be these kind of things, and the graph will be like that. So our solution was like this. As you remember, our solution is one of these corner points. So our best solution will be one of these corner points, and then we cannot have negative solutions. And we're going to add additional constraint called integrality constraint. So let's say we have x1 and x2, should be positive. Now x1 and x2 are integers. So this is our new constraint. So for now, from this, we know this point was our best solution, but this was not integer, and x2 was not an integer. So if you try to find integer solution from this example, maybe round up or round down of the solutions. So best solution was, what was it? So like you said, the graph, and if I draw that graph here, I have x1 and x2 using two decision variables, and this is a feasible solution. We know one of these corner points will be optimal solutions, and this is optimal solution for now, which has fractional numbers. Now to have integer, and here is 2. This, oh no, I got it wrong. Numbers. So this, let's say, is 2. Oh no. So that should be up here. 2, 2. So this is 3.0, and this 0.2. Now this is optimal solution. To find integer solution, we just need to round up and round down. So as you see, maybe 1, 2, 1, 2, 3 over here, right? And then the 3 point with the decimal values. So our integer solution will be round down or round up. Then we can find integer solutions. But now our integer solutions be 0.0, 1.0, 2.0, 3.0, 0.1, 0.2, 1.1, 1.2, 2.1, and this is not an integer solution, right? So this is not an integer solution. So we only have 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 feasible solutions, 10 feasible integer solutions. So which one is the best solution we are looking for? It can be this, or it can be this, which is the closest to the fractional optimal solutions. Right? You may try either of these. Yeah, my drawing is different from the slides, but you know what I'm saying. So would be one of these two would be our optimal solution. So you can have enumeration approach with objective function, but we can find best optimal solutions using solver. So when solving on linear programming relaxation, now we have new constraint, x1 and x2 should be integer. That's the integrality constraint. If we relax this constraint, we're going to have regular general linear programming. So we call it LP relaxation. Sometimes, if you get lucky, and obtain an integer feasible solutions like we had in the past couple of chapters. But this was the case in the original Blue Ridge hot tubs problem, in the earlier chapters. We had integer solutions, and also we had integer solutions from transportation assignment. But what if we reduce the amount of labor available from the constraint from 1520 to and the amount of tubing to 2650 feet, then the solution will going to be fractional numbers. So if you open the Excel files, you may see the solutions, which are fractional numbers. But let me just try to skip the file. The thing I want to mention, the optimal solution to an LP relaxation without integrality constraints of an ILP problem gives us bound on the optimum. And you see here, LP relaxation will give us optimal solution, which are fractional, sometimes integers, but our integer solution will be less than or equal to that fractional solutions. Because that's why it says linear program will be upper bound for maximization. If it is a minimization problem, that will give us a lower bound. You may try to find integer solutions by rounding feasible solutions, or round up, round down, then you'll find the solution very close to optimal solution, but that is not actually optimal solution, so we call it suboptimal. They can be local optimal or can be global optimal. So as you see from this graph, I have x1 and x2. If your feasible solution is like that, and this is optimal solution, then if you have integer solutions, right, maybe round down and then round down, maybe your solution is one of these, but this point is out of the feasible region, so this cannot be your solution. We have only one solution here inside the feasible region. So that's why I say integer linear programming solutions will be less than or equal to the solution from LP relaxation. To solve this kind of integer linear programming, we may use different algorithm called branch and bound algorithm, but we are not going in depth. Theoretically, this can solve any integer linear programming, but practically, if you have so many integer variables drilled down into decision trees, it will consume computer memories, so it's going to be slow. So may think of have a threshold to find the best solution. It doesn't have to be global optimum. It'll be suboptimal, but we're gonna find very close numbers to optimal solution. So we can set up the 95% of threshold to find solution, and you can set it up in computer programming. Okay, so now I'm going to maybe open Excel file, fix the charge problem. Okay. Right, so we're going to have an example of binary integer solutions using fixed charge problem. So many decisions result in a fixed or lump sum cost being incurred. For example, the cost of lease, rent, or purchase a piece of equipment or vehicle that will be required if a particular action is taken. So when it comes to total cost, the fixed cost plus variable cost, as you know. So variable cost is per unit cost. The fixed cost is exact amount of cost which will be spent, no matter what, how many product will be produced. So this kind of fixed cost, but between these two, there is a kind of sunk cost based on decision. If you don't decide to produce something, you will not be able to pay for this. But if you decide, if you have a particular action, then you need to pay for that. It is not per unit, but actually it's kind of similar to fixed cost, right? So this kind of problem we're going to use a fixed charge problem. That can be happen, and if you rent your car to go to Washington, D.C., and if you take a train, it is going to be a variable cost. But if you rent your car, you need to pay certain amount of fee per day and insurance cost, right? So it can be also setup cost. So once you start produce certain products, you need to open the production line. So you need to set up the line, right? So you have extra cost. Okay, so now from the example, Remington Manufacturing, they produce 3 different types of product. Product 1, product 2, product 3. Right? So producing these product, we need 3 different types of operations. Machining operations and grinding operation and assembly operation. So produce product 1, let's say X1, X2, X3. So these will be our decision variables. And to produce X1, you need 2 hours of machining operation, 6 hours of grinding, and 5 hours of assembly. To produce product 2, X2, so you need 3 machining hours, 3 grinding, and 6 assembly hours. And to produce product X3, you will need 6 machining hours, 4 grinding hours, and 2 assembly hours. But if you produce, we are shown you will be able to sell in the market. So the market, product 1, X1 will be $48. And product 2 will be $55. Product 3 will be sold at $50 in the market. That is a profit per unit. And but a little bit different things from chapter 3, 4, 5 is once you decide to produce X1, you need to set up the production line, product 1. So to set up the production line, the setup cost will be 1,000. And to set up the production line 2 for product 2 will be 800. production line 3, production line for product 3, setup cost will be 900. Okay, like we said, number of product 1 to produce will be our decision variable x1, and x2 will be number of product 2 produce, x3 will be product 3, so call it xi to make it shorter. The question is, what are the decision variables in addition to xi? So we decide which production line will be open. If we decide to produce product 1, let's call it y1. That means y1 should be 1 or 0. 1 means we're going to produce product 1. 0 means we are not going to produce product 1. So if you decide not to produce x1, then x1 should be equal to 0. So these two are linked. These two are linked. Now, if you open production line 2, that also will be y2 with 1 or 0 variable, which are binary. If the company decides to produce product 3, you need to open the production line y3 by the binary decision variable 1 or 0. So now we have 1, 2, 3, 4, 5, 6 decision variables. Let's call this yi. Now you have 2 groups of decision variables. Next step is to find object function. So object function will use decision variables. So what are the object function? So are you going to maximize or minimize? Maximize profit or cost? Profit, right? So in this case, profit is, let's say net profit. So profit minus setup cost. So what is the formula for profit? If we produce X1, then you will be able to sell product by 48. So 48 X1 plus 55 X2 plus 50 X3. Now, what is the total setup cost? Once we decide to open this production line, the setup cost is 1,000. So 1,000 Y1 plus 800 times Y2 plus 900 times Y3. So this is your object function, which is subject to okay, so I need to have large parentheses, or you may have minus for this. Thank you. Okay, how many hours do you have for machining operation? Have 600 and 300 for grinding and 400 for assembling. Now 2x1 plus 3x2 plus 6x3 should be less than or equal to 600. Now, for grinding operation, you need 6 hours for x1, 3 hours for x2, 4 hours for x3. That should be less than or equal to 300. You need 5 hours assembling hours for production 1, 5x1 plus 6x2 plus 2x3, so less than or equal to 400. Then we have we have second group of constraints. Because you have additional variables y1, y2, y3, then I said these two numbers are linked. Once we decide to open the production line, we're going to have a positive number, right? Then if you close the production line, that should be 0. So if you don't produce, this line should be closed. If you produce any number of x1, that should be open. These two numbers are linked. Do I need a space? So these are the linking constraints. That's huge. Small space here. How do you define that in math formula? Okay, for example, if we produce five production 1, if x1 equals 5, then y1 should be 1, right? And then if x1 equals 4, y equal 1, 3 equal 1, if 2 should be 1, 1, and then 1. If x1 is 0, y1, 0. Do you find any pattern from here? Right? So you try to maximize x1, to increase profit. Then x1 is not 0, so y1 should be 1. Then we just have example of 5x1, but it can be 100 if produced 100 x1. So instead of saying 5, let's say this is large M. So you can say 100, 200, 300. That means if you have 0, x1 will be 0. If x1 is 1, you will have maximum x1, which is similar to close to M. But that can be infinite. But actually, we can find the exact number for M. Now, if you don't produce x2, x3, then 2x1 will be 600, right? So maximum of x1 will be 300. So if you don't produce x2 and x3, you may be able to produce maximum 300 divided by 6, and 50 x1. And then if you don't produce x2, x3, your maximum number of product 1 will be 400 divided by 580. Now, if you produce 300, you violate these two constraints. If you produce 80, you violate this grinding constraint. So 50 will be the right answer to replace with M. So this M may be 50. So you can find the exact value of M. However, if you have negative numbers, it will be different and you cannot guarantee it. So let's say M is a very big number. It can be very big number, or you can say whatever you want to call arbitrarily large number. That's why I call it big M method. Big M method. Now, if you rewrite the constraints of linking constraints, x1 be less than or equal to my1, x2 should be less than or equal to my2, x3 should be less than or equal to my3. So this is equivalent to x1 minus my1 less than or equal to 0. So we have 1, 2, 3 constraints, and then the 3 linking constraints, and then x1, x2, x3 should be greater than or equal to 0. Now we're going to have an example of work scheduling. This is an example with Air Express company, and of course, I guess some of you working for HR department, maybe you can apply this. Okay, so we have days of a week: Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. We open 7 days a week. Then we need number of workers for each day of a week. Sunday, we need 18. Monday, we need at least 27. Tuesday, we need 22 workers at least. Wednesday, we need at least 26 workers. Thursday, 25. Friday, 21. Saturday, 19. The HR manager is setting up 7 shift, because you will work 5 days a week, and then each shift will have 2 days off. First shift will have days off on Sunday and Monday. Everybody's want to be off on Sunday and Saturday. So if you have off on Sunday, Saturday, your salary is lower than working the other days. So like you see, shift to 7, your wage is 65.5 per week. And then except Saturday, Sunday, Monday through Monday, Tuesday. Okay, so if you have only one Sunday or one Saturday from shift 1 and 6, your wage is $680 because you're getting $25 extra dollars for Friday. Then if you work Monday through Friday, you will get paid $25 per day, extra pay. So basic salary, yeah, wage is $655. Okay, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. Sunday, yes, Sunday. All right. So you can see Monday through Friday. So you have 2 days off. So that is a shift to 6. No, 7. This is a shift to 7. If you work from Monday through Saturday, Monday, so then you off will be Sunday and Monday. Sunday, Monday. So that's a shift to 1. Right. Then if you work from Wednesday to Sunday, your Monday, Tuesday will be off. Monday, Tuesday will be off. So this is shift to 2. You see, and the pattern. And for the shift to 7, your wage is $655. For shift 1, the wage is $680. And shift to 2, wage will be $705. Now, thing is, how many workers do you need on Monday?
18.
18.
27. 27.
On Monday, 27.
Yeah, I was looking at Sunday. Monday says 27.
Okay, Monday, 27. Tuesday,
22.
22. Wednesday, 26.
26.
Finally, Sunday, you need 18.
18.
Okay. So now you sum of these should be 26 on Wednesday. Are you following this?
Yes, we're following it, Professor.
All right, thank you. See, now just be careful with this diagram to understand about the work schedule. This is minimum number of workers. Right. So decision variables will be the number of workers assigned to shift 1. How many assign you? Okay, for example, if you just assign 25 on Monday, 25 on shift 7, you only have 2 workers from this different shift. Right? However, that doesn't mean all other requirements. Right? That's why I try to find number of workers assigned to each shift. So these are the decision variables to meet this requirement. So your objective function, I'm just trying to check 44. These are decision variables. Then what is the objective function? Minimizing wage, let's say wage expense. $680 for X2. So let's, oh no, this is X7. Oh, I'm sorry. No, don't need, right? X7. Oh, this should be X1. No, X1. Oh, this should be X1. Sorry. There was something wrong. Is X1, X2, X3. X1, 680 times X1, number of workers assigned to shift 1, plus 705, X2, 655, X7. This objective function is subject to what are the constraints? For Monday, oh no. For Monday shift, Monday shift, 0 from shift 2. Do you see that? Shift 7 will have workers on Monday, but shift 1 doesn't have workers on Monday. So let's start from shift 1. So 0x1 on Monday plus 0x2 no, only 2 days. Yeah, only 2 days. No, x1, x1, x2, yeah. 1 day and Monday, x7 is 1, right? 1x. Oh yeah, I have a wrong diagram because you have 2 day off, then you have, it's not day off. Yeah. Then 1, 2, right. Sorry, I gotta, yeah. 1, 2, right? Is empty, no workers. So 171, so 717. Plus 0x1, 0x2, 1x3 plus 1x4 plus 1x5 plus 1x6. 6 should be less than or equal to, less than or greater. Because this is minimum, so it should be greater than or equal to 27. Let's go with the Tuesday. Tuesday, x1 will be 1x1 plus 0x2, 0x3 plus 1x4, 1x5, x6, 1x7 should be greater than or equal to 22. Okay, we have under 5 minutes, so let's go with the Wednesday. Let's start from shift 1, 1x1 so 1x2, 0, 0x3, 0x4 plus 1x5, 1x6, 1x7 should be greater than or equal to 26. So you're gonna do these for Thursday, Friday, Saturday, Sunday. Then we know xi should be greater than or equal to 0. And also xi should be integer. We can say for all I. All right, guys, I'm gonna stop here and